Hi, welcome to question 8. So for the first part, it's going to be determining which sorting algorithm matches which particular sequence. And so each of these parts, A through E, are going to represent several intermediate steps. So not necessarily beginning or end, and they may not be consecutive either. Okay, so for a trick on how to approach these types of questions is really to just kind of spot the defining characteristics of each sorting algorithm. So for part A, and also just as a note, quicksort is going to have the pivot always be the first item. So for part A, let's see what's happening, right? So we have this sequence in the beginning, and then now we have 7 in the beginning, and let's see where 12 went. 12 went here. And for quicksort, a really great key characteristic is to see whether all the elements to the left of one element is less than that element and all the elements to the right of that element is greater than that element. And that's exactly what we have here, right? So we use 12 as our first pivot because again, pivot is always going to be the first item in our scenario. And all these elements are less than the pivot and all the elements to the right of 12 are greater than. So this must be quicksort. And in fact, this is correct because if you look at the next sequence, now we know that the 7 is going to be the pivot of this subarray, right? And in fact, these left numbers are less than 7 and these right-hand numbers are greater than 7. So we can say that this is quicksort. Okay. All right, so for the next part, so we've eliminated this, right? For the next part, the thing that I'm noticing is that all of this stays the same, right? But now this became sorted. The first half became sorted. So why is this the scenario? Which sorting algorithm can sort in this fashion, right? Start from the very beginning and sort as you go to the end. That is actually insertion sort. And the reason for that is because insertion sort starts at the very beginning of your array, and for each succeeding element that you haven't looked at yet, it handles all the inversions if there are any, right? So what happened is that we looked at 23. The first element is always sorted because we haven't looked at any other. Then we look at the 45. The 45 is greater than the left element, which is 23, so we're okay. It's in sorted order. Then we look at the 12. The 12 is not greater than its left element, 45, right? So now we know that we have an inversion, in which case we need to flip 45 and 12. And so now it's going to look like 23, 12, and then 45. And then we have 4, and then the remaining 4 elements, right? And now we're looking at 4. That's the only element that we haven't looked at so far. Oh, sorry. Actually, we need to actually continue on with 12 to make sure that we have handled all the possible inversions. So after we switch to 12 and 45, we check whether 12 is now greater than its left element. In this case, it is still not greater, and so we need to flip 12 with 23, and so this. And now we need to work with the 4, okay? So is 4 greater than its left element? No, so now we need to switch 4 with 45. Okay, we're still looking at 4. Is 4 greater than its left element now? No. Okay, so now switch those two. Is 4 greater than its left element now? Still not, and so we know that 4 is going to be the first element of this array. And that's how we arrived at this sequence, right? So we skipped some steps here. It didn't show those steps, but that's how you got there by insertion sort. And that's why these remaining 4 elements didn't get changed at all, right? We were only able to work with the remaining sorted subarray with insertion sort. How about for part C? Part C looks like it has, okay, so one thing that I'm noticing is that all of these start with 1, this start with 2, these start with 3. Okay, well, that is in sorted order, right? The first digits are in sorted order, and so that must mean that it's by MSD, the most significant digit. The least significant digit is going to be to the right digit of a number. And so this is going to be a radix sort, okay? So if nothing strikes the bell, try to just kind of go through process of elimination, apply a sorting algorithm, see if it fits that characteristic. And luckily, I was able to find that with MSD. For part D, I instantly noticed that these have been swapped. This is the same. These have been swapped. These have been swapped. Well, that reminds me of merge sort, right? Because remember when I hit the base case for merge sort, that's when I have to merge two one-element arrays, right? And in this case, in the first case, they were not in the right order, so I had to swap them, which is how I got to this second sequence. And then from there on, I need to merge two-element arrays, right? So really, if I'm consistent with my bracket notation, it's going to look like this. So this is going to be my final result of merging these two-element arrays twice, okay? And then finally, the final step is not really shown, but now I'm going to have this entire array resulting, right? Okay, so I think my notation might be a little bit confusing, so let me go back. So the lines are going to be drawn between the two components that we're trying to merge. Okay, so here we're looking at two one-element arrays, and so these are going to be the components, but the blue brackets are going to denote the final merged component, and not in that order, but you know, the size. And then similarly for this level, and then for this level, okay? All right, so what does that leave me with? Well, usually heap sort is kind of the hardest to find, but there is a trick. So heap sort is either going to use max heap or min heap, okay? So if it wants to sort it in, so here it's going to be using max heap because we have everything in this step less than as you go to the right, right? So 54 is going to be our root, which means that it's the biggest element, and so that's going to be a max heap. And in fact, we do put it at the, we do put it at the very end here. Sorry, let me actually scroll up a little bit. We put it at the end here, right? Okay. And so what does that mean? Well, we're building our array from right to left, okay? And if I'm removing the root at every iteration and then bubbling up or bubbling down as I need to, and my root happens to be the biggest element, well, that reminds me of max heap, and that reminds me of heap sort.